you all?
Hello.
How about now? All right, you hear me now? Great. Thank you for letting me know. Thank you. I appreciate it. All right. I have a very old webcam and I've bought a couple of new ones, but I don't like them as well. I feel like they're like I have a better picture with this old one, but once in a while the sound cuts out. Interestingly, once in a while it makes me sound like a chipmunk. So please don't ever let me just teach the whole class sounding like a chipmunk. Let me know if that happens. All right, if you have no questions, we will begin our class today. All right, let me know if you can't see that. All right, it says physical science. All right. So I want to give you guys a heads up. You may have noticed if you've looked ahead, we will be doing some oral presentations in this class, just one in the whole year. So we'll have it right off the bat in November. We'll be doing this. So your presentations will be, because we've got a bigger class, we had to split it into two different weeks. So some of you will go on Tuesday, November 11th. That's 2 weeks from today. And some of you will go on the 19th. That's 3 weeks from today. So I just basically divided you down the middle. If your name is under the column that says November 12th, you will go the first week. That's 2 weeks from today. If you're in the second column under November 19th, that's when you'll do it. So this is in the lesson. You'll notice that there's a lesson that gives you all the information that you need in order to prepare for your presentation. So you have 4 different options that you can pick. You pick one of those options. And if you have any questions at all, please contact me sooner rather than later so that you don't prepare for a lesson, prepare the wrong thing. So make sure that you do that. Okay, anybody have any questions about the presentation that you're doing? It's just, maximum of 5 minutes, so not a long one. Most people take 3 minutes, I would say, is about the average. So this doesn't have to be anything really long. Mel.
What is it going to be about?
So the lesson, I'm not going to go into the details about it now. You can find the lesson in the classroom. I'm going to pull that up and show you. So you have options. There's a math option. It's all about soap. That's what the whole thing is about. But you have a math option where you can calculate the amount of soap needed. There's a science option. Let me do this here. So here we go. So write down, where are we right here? Instructions for oral presentation. Okay, so if you guys are in section 1, so you're going to click right there and it will tell you what you need to do. So that you read all this, and then this is the people on November 12th. This is November 19th. Yes, it is required. It's worth 40 points. This replaces the unit exam. You do not have to do all of them. You pick one. And then down here, it tells you, if you pick your science option, you're going to make homemade soap and talk about it. If you pick the social studies option, you're going to make a timeline and talk about it. The language arts, you're going to write a historical fiction narrative and talk about it. Math, you've got some calculations and then you talk about it. Okay, so hopefully all the details that you need are there. Read it over, and if you have any questions, don't hesitate to contact me. All right. All right. But what we're going to talk about today is some science basics. So what do you think of when you hear the word science? What is science anyway, besides your favorite subject? Josiah.
Basically picking apart, prodding, and burning everything natural to try to make something unnatural.
Picking apart and burning? Is that what you said?
Picking apart, prodding, cutting, basically just doing stuff to nature. Also, basically just like,
Well, you're definitely on the right track. We do stuff to nature, not always. Science doesn't always involve doing stuff. It's basically about learning about nature. Sometimes, though, you're right, it involves experimentation, doing things. In fact, I think the best science is when it allows me to do stuff. So the definition of science is learning about the natural world. And that is based on evidence and logic. And, of course, the evidence comes from experimentation often, not always, but often. So there's a lot of different science fields. You guys named a couple of them there. Saxon said physics, Richmond said chemistry. We've got biology, we've got astronomy, we've got earth science, we've got engineering is a field within science, life science. Yeah, exactly. So one thing that they all have in common is that they're all always changing, right? Science changes. Sometimes the change happens real fast in just one step. We learn something completely new that changes what we thought we understood. Sometimes it's slower, sometimes even tiny baby steps. And if you look back throughout history, a lot of new ideas are not always accepted. And really, the scientists might even be mocked for their ideas. So can you guys think of a time when that happened? Can anybody think of an example of when a scientist was not accepted? Josiah.
Galileo, I think.
Yeah, Galileo is a good example. What else? So there was a guy whose name was Lister, Joseph Lister, and he had an idea that germs on doctors' hands might be causing diseases in people. So he suggested that the doctors start washing their hands when they went in between doing an autopsy on a dead body and a birth of a baby. Seems pretty logical to us now, doesn't it? But he was actually scorned for that idea. People didn't accept that idea at all. There was a scientist named Wegener. He suggested that at one point, all of the continents were, well, good question, Ellie. Why do you think? If you had to guess, why do you think? Mel.
Because people like to think the way that they think and they don't like change.
Yep, that's a big part of it.
The ridiculous land bridge theory was more accepted. Or literal land bridges that look like highways, cartoon highways. Literally, people drew it. It was real.
Yep. Richmond?
So I remember when we were having this history lesson and we were talking about when everyone thought that we were at the center of the universe.
Yep. Yep. So there was a scientist named Copernicus, and he was the one who said, no, it's not a geocentric universe, meaning Earth in the middle. It's actually a heliocentric universe with the sun in the middle, and all of our planets go around the sun. And he was scorned. I mean, he took a lot of heat for that. Yeah. So the one I was talking about, the Wegener, he suggested that at one point, all of our continents were one. They were a big Pangea. You guys have heard that, Pangea. And that they migrated, they moved over time to where they are right now. They called that continental drift. That wasn't accepted at all. I mean, really, history is filled with examples of people who were not accepted at their time. Sometimes even in their whole lifetime, they were not accepted. And then later we found out that that was true. Science changes. And as scientists, you guys need to have open minds. You need to be willing to accept that what you think you know might not be true, that we might find more information that disproves some of the things that we think right now. So another thing that all the sciences have in common is that what scientists do is investigate. So we use investigation or experimentation or studying as a way to gain more knowledge, to gain a better understanding of the universe, of the world that we live in. So these investigations, these scientific investigations, they produce evidence that helps to answer our questions. So even if the evidence can't necessarily answer a question, it still is often useful. So one really good example of this is Mendel. So Gregor Mendel is called the father of modern genetics. And if you ever take a life science class, you'll learn about him, or a biology class, you'll learn about Mendel, because he started all of our genetics, the research that we do right now. He began it all. But a lot of what he thought at the time was wrong. We've now learned more and we know more than we did when he was there. So even though his evidence gave us incorrect answers, in many cases, it was still very useful because it got things started. And he did really good note-taking and research, and that's really critical when you're a scientist. So a lot of times, even when, you know, I've told you guys before, sometimes when you learn more from an experiment that doesn't go the way you think it will, than you do one that does. Because a lot of times something going wrong leads us to more questions. And as more knowledge is discovered as a result of trying to answer questions, science moves on, science advances, and that's what we're all about here. So how do we get this information anyway? How do we investigate? Well, scientists use a lot of different methods to investigate, and in different fields of science, they might use different methods. Obviously, astronomers, when they're studying the stars, they can't look at them under a microscope. They can't take pieces of them and mix them with other elements, but they use different methods in order to be able to get the information that they have. Most science, though, is going to follow the general steps that you can see in this picture. Most scientists follow, or at least base their work on, what we call the scientific method. Starts with an observation. You see something, usually with your senses, or a tool that extends your senses, like a microscope or a telescope. So you observe something, and that leads you then to ask a question. I wonder, why have I see this? What would happen if I did something? You ask a question. Then you do some research to see if somebody else has already answered your question. Maybe somebody else already knows. Then you make a hypothesis. We're going to talk in detail about hypothesis in a second. Basically, a hypothesis is an educated prediction about what you think will happen if you do something. If you do that something that we call the experiment. So you run your experiment, you collect your data based on the experiment that you did, what you get as a result of the experiment. Then you either accept or reject your hypothesis based on the data. You come to a conclusion and you share your findings. You present a report. So the whole scientific method basically can be considered a process. It's those steps that we follow in order to find answers to questions about the world that is around us. So is there only one scientific method? No, there's actually a lot of different versions of the scientific method. Some of them have more steps, others might have only a couple, but they all start with the same kind of identifying a problem, making an observation, some kind of question that has to be answered based on something going on in the world around you. So let's break down the steps of the scientific method. It gives us this organized way to conduct and analyze an experiment. Here are the steps again, looking at them right here. Step 1, observe. An observation, basically, that's any information that comes in using your senses. So sight, sound, smell, touch, taste, although be very careful, don't taste things in a science lab. You need to be careful touching and smelling things if you don't know they're safe. But we use our senses in order to make observations. And we sometimes use instruments, things like thermometers, measuring utensils, like I said, microscopes, telescopes, even computers can be used to extend our senses, to extend our ability to make observations. So I want to go through these different steps, starting with observation using a real life example. So here we have a blacksmith. Let's suppose that a blacksmith reads about a new kind of synthetic fuel that is supposed to make a hotter fire. All right, what's the observation? Josiah.
He's heard about, like, he's heard with his senses about this new fire, and he's probably seen it, that it makes hotter.
Good. So this new synthetic fuel is available. That's what he's observed. He's observed, oh, there's something that I can use that's new that might make my fire hotter. So the next step then is to ask a question. What might his question be? Based on the observation that there's a new kind of synthetic fuel that will make a hotter fire. Matthew.
Why is it hotter, or what makes it hotter? Or even why do I need this?
That's a possibility. Yeah. Yeah. Josiah.
Maybe how hot can it go, or would it damage anything?
Okay, good, good. So those are all good ones. So the why is it hotter? That's a good question. That's absolutely a good question that he would want to find out. That's not one that would be based on the question that he on the observation. Remember, his observation was there's a new kind of synthetic fuel that will make a fire hotter. He wants to know, will it? Is that true? That's his question. Will it burn hotter than coal? So now his next step is going to be research. He might do some research to try to figure out whether or not this new synthetic fuel really does burn hotter than coal. He can read about it. He can ask some experts about it. He can go online. He can do whatever research he can in order to find out what other people already know about it. So now our next step is what? What comes after research? Mel.
Hypothesize.
Yeah, he's going to make a hypothesis. So a hypothesis, big word. Basically, it just means educated prediction. You'll sometimes hear it called educated guess. I don't like that because it's not a guess. I prefer the term educated prediction. An educated means that it's based on something real. It's based on something that could really be. And it is based on what is observed and what you already know about the topic that you either got yourself or that you got from your research. So an educated prediction is about what's going to happen. Now, there's a couple of really important details about a hypothesis. It has to be testable in order to be useful. That means that we have to be able to do an experiment to see whether it's true or false. So for a hypothesis to be testable means that it's possible to make observations that either agree or disagree with it. If it can't be tested, it's not scientific, right? It's not a good hypothesis. So think about this one. Think about this statement right here. There are invisible creatures all around us that we can never observe in any way. Is that testable? Might be true. There might be little microscopic life forms around us in the air, but if we can never observe them in any way, they're invisible, we can't test that. So that's not a scientific hypothesis. So when we're given a hypothesis, there have to be some things that a scientist can do in order to test whether they're true or false. And along those lines, it also has to be falsifiable. What does that mean?
You can prove it wrong?
Yeah, you have to be able to prove it wrong. It might be testable, but even that isn't enough for it to be a truly scientific experiment. We have to also be able to show that it is false, if it really is false, right? So think about this statement. There are other planets in the universe where life exists. Is that testable? I mean, kind of, theoretically, yeah. It's at least theoretically possible that we might find evidence showing that that's true. There could be a spaceship that's sent from the Earth to explore the universe, and it comes back and reports whether or not we find an inhabited planet. So if this planet were found, it would prove the statement true, but the statement isn't scientific. Because if it's false, it's not possible to show that it's false, right? We can't falsify that. That spacecraft could travel for 1,000 years and never find an inhabited planet, but that doesn't mean there isn't one out there. It just means that maybe it needed 1,001 years in order to prove that. Given how huge the universe is, it may never find one, but it might be there. So that's not a falsifiable hypothesis. That makes sense to everybody? They have to be able to prove that it's false. So here's an example. Any two objects dropped at the same time from the same height will reach the ground at the same time, assuming there's no air resistance. Can we test that? Is that testable? Yeah. Yeah, that's testable. All we do is do it. We just drop two objects at the same time from the same height, and we observe when they reach the ground. We have to make sure there's no air resistance. But if that's true, then testing that is possible to do. Is it falsifiable? Yeah, it is. We can easily test many combinations of two different objects. And if any two of them don't reach the ground at the same time, then our hypothesis is false. So if a hypothesis is false, it should be pretty easy to disprove it. All right. Another thing about a hypothesis, whenever you possibly can, you want to write a hypothesis in if-then format. What I mean by that is, if something is done, then something will happen. Let me give you a couple examples. If you get at least 8 hours of sleep, then you will do better on tests than if you get less sleep. So that tells me what I'm going to do. The if is what the experiment is, getting 8 hours of sleep. Also tells me what I'm going to look for. I'm going to look for improved test scores, right? If then, that's the magic of the if then hypothesis. It tells us what we're going to do, and it tells us what we're going to measure or look for. Here's another one. If you drop a ball, then it will fall toward the ground. Is there a wrong way to form a hypothesis? Yeah, Ellie, there is. There are some ways that are better than others, and there are some ways that are just wrong. If it's not testable, if you write it in such a way that it can't be tested, then that would be a wrong hypothesis. I like you guys to use if-then format. I always teach my classes to use if-then because it tells you what your experiment is and it tells you what you're going to look for in your data. It's a really, really powerful tool. Yeah, I don't know coding, Matthew, so I used to write code 20 years ago, but I have no idea what it's
I
like
think
now.
it's basically like that. Basically, one of the variables. It says if this happens, then this will happen.
Yeah, like if I type a star, then everything will glow. Yeah. All right. So if you drink coffee before going to bed, then it will take longer to fall asleep. What am I going to do? The if, drink coffee. The then, how long does it take to fall asleep? All right. If I heat my water before adding sugar, then more sugar will dissolve in the water. If I do this, that tells me what my experiment is, heating my water before adding sugar. What am I looking for? The sugar to dissolve. All right, now let's look at a hypothesis for this synthetic fuel. Anybody have any thoughts? Remember, our observation was he read that there was some synthetic fuel that burns hotter than coal. The question was, will the synthetic fuel burn hotter than coal? What is the if-then hypothesis going to be? Josiah.
If the synthetic fuel is real, if the synthetic fuel burns hotter, then the metal will warm up faster or melt faster. Okay,
you're really on the right track and right on the edge. The way you said it, though, doesn't give you what you're going to do. If the synthetic fuel burns hotter, that isn't something that the scientists can do. I want my if to be what we're going to do. We're not going to burn it hotter. So what are we going to do? Go ahead, Josiah.
If the synthetic fuel burns hotter, then it should, wait a minute. That's wrong.
Take out the burns hotter.
If the synthetic fuel is hotter.
That's still not something we're going to do. You're walking around the edge of the basketball hoop, Josiah. You just need to fall in. Yeah. Luke.
If it is true that the fuel burns hotter, then the work will become faster because the metal is burning fast.
Okay, once again, you're walking around the edge. It burning hotter is not something I'm going to do. Think about what I'm going to do.
Fuel burning?
What?
With the fuel burning hotter?
Again, real close. Mel.
If I put the synthetic fuel in my oven, then it will burn hotter.
There you go. What am I doing? I'm using the fuel. I'm putting it in my oven. What am I looking for? The increased temperature. Got it? You see how just that little bit of change, you guys were right on the right track with that. But when we change the wording, so it tells me exactly what my experiment is going to be. So I did this one. If the new synthetic fuel is used in a forge, which is the oven that you use when you do blacksmithing, then the fire will burn hotter. That tells me what I'm going to do. Use the fuel in my forge. It tells me when I'm going to measure the fire getting hotter. All right. That makes sense to everybody. All right. Now, the next thing we're going to do is the experiment. Writing our if-then hypothesis this way tells me what my experiment is going to be. This is the real magic of it. All right. Tells me what I'm going to do. Use the new synthetic fuel. Tells me what I'm going to look for, the fire to burn hotter. All right. Now, part of the experiment is going to involve changing some things, but not changing others. The things that could be changed in a science experiment are called variables. And there's 3 different kinds of variables: independent variable, dependent variable, and controlled variable, sometimes called constants. Let's look at each of these now. An independent variable is something you change. It's something that is changed by the scientist. What are we changing in our blacksmith experiment? What's the one thing we're changing? Josiah.
We're changing the fuel from coal to this new synthetic fuel.
Exactly. So the fuel is going to be our independent variable. That's what we're changing. The dependent variable is what we measure to see the effect that our experiment had. What is it here? What are we going to measure in this experiment? Luke?
The temperature.
Absolutely. We're going to measure the temperature of the fire. We're going to see if it's burning hotter. Now, we've got our independent variable as the thing we change. The dependent one is what we measure. We've also got a lot of things that we have to keep the same. Controlled variables are variables that are not changed. So as we're running this experiment, we need to make sure the only thing we're changing is the fuel. If I, for instance, used, like I did one experiment, I had my, I tested coal and then I tested the new fuel. But in the new fuel, when the forge was a lot bigger and it was a windy day and cold, as opposed to a hot day that there's no wind. Can you see how those variables would affect the experiment? Right? So I want to make sure nothing else changes. So in a controlled experiment, you have your independent variable that you change. Your dependent is what you measure. What are the controls? Everything else. That's the right answer. When you say, what are the controlled variables in this experiment? Everything that I'm not changing is a control. I want to try to keep everything the same in the experiment. So those of you who have been in my classes before know this guy. This is a silly but helpful way to remember the different kinds of variables.
Independent variables are the ones you change. Independent variables are the ones you change. Dependent ones are what you measure. Controls will stay the same, whatever. Independent variables are the ones you change.
Yeah, I like this song because all you really have to remember is the first part of that song. Independent variables are the ones you change. That's it. You already know what the word control means. It's something you keep the same. If you can remember independent variables are the ones you change, then you know that the dependent is what you measure. If you can remember that song, that'll really help. Now, to confuse things a little bit, some resources will use different words. They'll use words like manipulated variable, but I bet you guys can figure out which one is the manipulated variable. You think it's the independent, the dependent, or the control? Manipulated. Mel.
The independent one.
Yeah, it's the one you manipulate or the one that you change. Good, good. All right, so now we've got our hypothesis. If the new synthetic fuel is used in a forge, then the fire will burn hotter. We know that the fuel is our independent variable. The temperature of the fire is going to be our dependent variable. And we're going to control everything else. Now we're going to conduct this experiment. So we could, you know, use the fuel in the new, the new fuel in the forge, and then we measure it. That's how we're going to conduct our experiment. Now, when we do an experiment, we usually like to have something to compare it to. So we're going to do 2 experiments at the same time, one with coal and one with the new fuel, and we're going to compare them to each other. The only thing different between the 2 is the fuel that we're using. One is coal, one is the other. And then we're going to gather the data from these experiments. We want to run the experiment multiple times because just running something once is no indication that it's actually true. It could be just a fluke. So we want to run it a few times. And then our next step after doing our experiment, after testing it, is to gather this data and look at it. So when we say data, what we mean is the information that we got from our experiment. We often will put our data into data tables or data graphs because it's a whole lot easier to understand something in a table or a graph than it is just a paragraph. Okay, so imagine if I had a paragraph that said 2 students preferred red juice, 8 students preferred orange juice, 10 students preferred yellow juice, and 6 students preferred purple juice. You'd have to read that and do a little bit of analyzing, but if I have it right here, you can tell at a glance, more students preferred the yellow juice than any other juice. Now, there's a lot of different ways that we can graph data, a lot of different kinds of graphs that we can use. Here's a line graph. Like it sounds, a line graph uses a line. Any of you guys worked with line graphs before in your math classes or science classes? Yeah. So line graphs are really good to show small changes and patterns in data or relationships between 2 sets of data where one set relies on the other. Basically, what we do with a line graph is we put our points on there and then draw a line that connects them. Another kind of cool kind of graph is called a circle graph. Sometimes it's called a pie chart. And a lot of times we use this with percents. So you have to remember that it has to add up to 100 because you have to have 100%. So just at a glance, you guys can tell if I said to you, what is the biggest cost of construction of a house? Mel.
The labor.
Yeah, the labor. It's 1/4 of the cost, bigger than any of the other pies that are on this pie chart or circle graph. So the size of each pie piece right there, of each slice of the pie, is going to correspond to the percentage. This is a useful way to do it. Another one that you can use to show the frequency for a set of data is called a histogram. So it compares data ranges. It does have bars, but notice how the bars in the bar chart are separated from one another. The ones in the histogram are not. They're right up against one another. So the bars that touch, there's no space between them. We're not going to go into detail about when you would use all of these, but just understand these are different ways that we can do. One of my favorites is called the scatter plot, and it looks just like it is, like somebody just scattered a bunch of spots on this piece of paper. Now, just like a line graph, a scatter plot can have 3 types of relationships. Things can be positively related or negatively related, or they cannot correlate at all with one another. But notice there's no lines connecting these. Instead of having lines connecting all of these in a scatter plot, you use what's called a trend line. So this would be a trend line right there. It shows the general trend of the data. So I could look at this, I could say, this data is trending upward. If it was going the other way, it would be this data is trending down. So here you can see an example of a line graph that is comparing 3 different data sets. So it asks you, which plant grew the most? Okay, which plant grew the most? Now, when you first look at this, you might think it's A because A is the tallest at the end, but that's not what it's asking. It's asking which grew the most. What was the plant growth rate? So take a look at A. It started at 30 right here. This is A, the blue one. Let me get my red pointer. That'll make it easier to see. A is the blue one. It started at 30 centimeters and it went up to 100 centimeters. So how much did it grow? Luke.
70.
70 centimeters. Good. Now look at B. B is the red one. It started at 10 centimeters and it grew to about 95. So it grew 85 centimeters. Now let's look at C. C's the green one. It started at 20 and it grew to 60 centimeters, right? You guys see how it's different there. So it would actually be B that grew the most. A grew 70, B grew 85, C grew 40. So B is the one that grew the most. You have to know what a graph or a chart like this is asking for. Make sure that you understand what it's asking for. Here's another one. So let's review this one. This question asks you to calculate average temperatures. So anybody know how you calculate average temperatures? If you've got 3 different temperatures, how do you figure out the average of them? Well, this would be this way. Josiah.
What you do is you add them all together and then divide by 3.
Right. You divide by the number of data sets that you have. So this is an easy one. They're all 22. So our average is going to be 22. So let's look at Lake Mary. We got a 19, a 24, and a 26. What's our average going to be there? Anybody want to do the math? Lainey.
I believe 13.
It is going to, not 13. You're close, but no, I mean, yeah, you got it, Mina. That's going to be 23. See, you got to look at they're 19, 24, and 26. So we know that the average has to be between the highest and the lowest. So the lowest is 19, the highest is 26. The average has to be between those two, somewhere in between. You can't have an average that's lower than one of the numbers. Right? That's okay. Yeah, you don't have to be a math person. This is science class. I'm just showing you how you can use these. All right, now take a look at this one. Another heads up. So this data table has the same values on it, but it's not the same data. It's not the same data. So this is asking for average temperature right here, where, let me see here. Calculate the average temperatures. This is asking for the range in temperatures. What is the range in temperatures? So the range in temperature differences for Fossil Spring is going to be 0. There's no difference, no range. Lake Mary, there is going to be a range. From 18 to 25 is 7. So we're going to have a 7-degree range. And the same thing for the Verde River. So you have to be careful. That's my whole point in all this, is you got to be careful reading your data tables. All right, now probably the 2 most common kinds of graphs that we use in science are bar graphs and line graphs. So a bar graph is used to either show how something changes over time or to compare different items. Every graph, every bar graph, and also the line graphs, they're going to have an x-axis and a y-axis. So the x-axis is going to be the one across the bottom. It's horizontal. The y is going to be the one up the side. It's going to be vertical. I'll show you guys how I remember what the x and y axis are. I picture a letter Y right here going like this all the way down. There's my letter Y. So the long part of the Y is the y axis. If I can remember that's Y, then I can remember that this one is X. Just a way to remember. That's how you remember it too, Ellie? Yeah. Yep. All right. Now, the X axis, that's going to be the one across the bottom. It usually has time in it or what is being measured. So in this one, what's being measured are the sports. Sometimes it'll have time as well, like as time passes. The y-axis has numbers for the amount of stuff being measured. In this case, we're measuring the number of students that we have. All right, and it is good for plotting data that spans over a long period of time, or really big changes, or when you're comparing things. That's what a bar graph. And you can see sometimes bar graphs go sideways, like this one, going to go that way. And sometimes they're up and down like that. But they're both called bar graphs. They're both very useful. Now, what kind of graph is this one? It says it there. Sorry, line. These are line graphs. So line graph can be used to show how something changes over time. Again, we have our x-axis down here, and our y-axis right here. Same thing. The x usually has the time period on it on a line graph, and the y has numbers for what it is that we're measuring. You can use these line graphs when you're plotting data that has ups and downs, like this one. You know, this temperature in New York City goes up and then down, and then up and then low, and then up again. All right. Or that was collected in a short period of time. And it's often used for two sets, like time and temperature. That's what we can see right here, time and temperature. All right. Now, usually blacksmiths cook coal until most of the impurities are burned off. And what's left after they're done cooking the coal is a fuel called coke that is almost entirely carbon. And it allows us to get up to really hot temperatures, somewhere between 3,000 and 4,000 degrees Fahrenheit at the core of the fire. So if we did our experiment and these were our results, somebody read the results. Tell me what you see on this bar graph from our actual experiment. Josiah.
So what it seems like is that the coal burns at around 30 to 35, so I guess it maybe around 34,000 or 3,400 degrees.
Yeah.
And the synthetic fuel burns around 4,500 degrees.
Good.
So there is a 1,000% increase in temperature.
Good. So if these were our results, was our hypothesis supported by our results? Yes? No? Remember what our hypothesis was. Our hypothesis was if the new synthetic fuel is used in a forge, then the fire will burn hotter. Was our hypothesis supported? Got a thumbs up from Matthew. Yes, our hypothesis was supported. But what if these were our results? If this is what we got, would our hypothesis have been supported? No, it would not. So what would we do? If we ran this experiment and this is what we got, we would go back to the drawing board. We'd have to make a new hypothesis and we would have to start over again, right? Now, after the experiment is over and we've collected our data, now it's time to come to a conclusion. So the conclusion is basically a conclusion tells again briefly what you did in the experiment and the results or findings based on the data that were collected. Basically, what does it all mean? What can you conclude as a result of it? Now, you also, in a conclusion, when you write a conclusion for like a lab report, you're also going to recommend further experimentation. What might you do differently the next time? What mistake might you have made this time? If you were to repeat the project, how could you extend it? How could you make it more or sharpen it up a little bit? And that's our conclusion. And there we have it. Those are the steps of the scientific method. We make an observation. We ask a question. We research. We develop our hypothesis. Whenever we can, we use if-then format because it tells us our experiment and it tells us what we're going to look for our data. Then we design our experiment. We test our hypothesis with our experimentation. We organize our data and we draw our conclusions and then we publish our results. And that's the scientific method. Anybody have any questions about that? Hopefully by this time you guys have had the scientific method a couple times in a couple different science classes. You will use it all the way through your scientific life. If you go into a science field, you'll continue using this. You'll continue doing it even at the the professional level. If you go into any kind of science field professionally, you give presentations and the presentations will be based on the experiments that you ran, the data that you collected, and what you can conclude based on that. So knowing the steps of the scientific method and how to use them are important. Anybody have any questions? Okay, I want to do a couple of practice scenarios. All right, so let's try this one. Suppose you wanted to know whether M&Ms would dissolve faster in your mouth using the variables of saliva, teeth, and tongue. So basically, you want to know whether dissolving happens faster with assistance from your teeth and your tongue or without, right? You get it? let's think of an if-then hypothesis for that. I'm glad, Ellie. Some people really like graphs, other people don't. I kind of think they're cool. I'm a graph and chart person. All right, Mel.
If I use my tongue and teeth, then the M&M will dissolve faster.
Very good. Excellent. That tells you what you're going to do, and it tells you what you're going to look for. You're going to use your tongue and your teeth to help dissolve the M&Ms, and you're going to measure whether or not it dissolves more quickly than with saliva alone. Very good. All right, so what are we going to do for our experiment? We know because of the if part. Mel.
You can have you could have two people, one person who just had the M&M sitting in their mouth and another person using their tongue and their teeth.
Okay, that's good. However, do you see a problem with that, Mel? If you have two different people, you've now introduced another variable, right? We want the only thing we change to be whether or not you use your tongue and your teeth. So you want to have the same person do it. Two different trials, but using the same person for the variable. So what we could do first is that we could place one M&M in your mouth and just allow it to dissolve without using your tongue and your teeth to help. And you then record the time that it takes for that candy shell to dissolve away. All right. Then you're going to place another M&M in your mouth, and you're going to allow it to dissolve using only your tongue to move it around, and you're going to measure. And then trial 3, you might place another M&M in your mouth and use your tongue and your teeth and dissolve it. All right, so if we do this, what is our independent variable? Matthew.
I just had a question
Yep.
about this. Isn't there a variable of like, first of all, maybe genetics of some kind, or that kind of thing, like how much saliva you produce,
Yes.
or how much saliva is in your mouth at a time?
Yep.
Isn't that a variable?
It is a variable. That's one of the reasons we want to use the same person for both. Because even though you and Mel are siblings, you might have a different amount of saliva that you produce. Your saliva might be more acidic than hers or less acidic.
But
absolutely.
What happens if, like, when I'm like trying to chew for the chewing one, if I produce less saliva, and then when I just let it sit in there in the same period of time, I produce less saliva or more saliva?
So that's true. And that's one of the reasons that when we do an experiment, we want a large sample size. So you might want to do this with 100 people. I mean, this is a silly example, right? We all know it's going to dissolve faster when you chew it than it will if you do it. But if you're doing a real science experiment, you want to have a large sample size so that you can take averages of all the different people. Good question. All right, so what is our independent variable here? Josiah.
The teeth and tongue.
Teeth
That's
and
what
tongue. Yep, absolutely. If we ran 3 different trials, one used just the tongue, trial 2 was just the tongue, and trial 3 was the tongue and the teeth, we've actually got 3 different things that we're testing here. So we're running like 3 experiments at the same time. But regardless, the independent variable is the use of the teeth or the tongue. So what then is the dependent variable? Josiah.
The dissolving rate of the M&M.
Excellent, excellent. All right, so we've got a solvent solute solution thing going on here too, right? You guys remember those terms. What is the solute in this experiment? Ellie.
The M&Ms. Wait,
M&Ms.
the M&Ms.
Yep, excellent. What's the solvent? Mel?
The saliva.
Very good. Excellent. All right. So suppose we got these results. Trial 1, just dissolving, just letting it dissolve in your mouth, 95 seconds. Trial 2, this is with using the tongue to move it around, 40 seconds. Trial 3, tongue and teeth, 25 seconds. Was the hypothesis supported? Yes, the hypothesis was supported. All right, let's do another one. Students of different ages were given a jigsaw puzzle to put together. The scientist wanted to see if the students' ages affected how long it took to put the puzzle together. What is our independent variable? All right, James and Mina, yeah. The age of the students is going to be the independent variable. What is the dependent variable? Mel.
The jigsaw puzzle.
So close. Let's look again at the. We can't really measure the jigsaw puzzle. What are we measuring? Yeah, you got it, James. The time it takes to solve to get the puzzle together, to put it together. What are the controlled variables? Remember what I said? What's the answer to the controlled variables? Ari.
Everything else.
Everything else. Yeah. We want to make sure that we use the same puzzle for all of them. Right? Mina, you got it. Education, Matt, that's very true. It wouldn't be fair if some of the participants had an easy 30-piece puzzle, but others had a harder 1,000-piece puzzle, right? We want to make sure they're all in the same location, that we use the same stopwatch every time, that the same person is timing the experiment. Yeah, that the temperature in the room is the same. We don't want it to be 95 degrees in one room and 25 in a different room. Very good. Excellent. All right, I think we have time for one more here. An investigation was done with an electromagnetic system made from a battery and wire wrapped around a nail. Different sizes of nails were used. The number of paper clips the electromagnet could pick up was measured. Okay, look at that again. Think to yourself what the variables are. What is the independent variable? The thing you change. What is the dependent variable? The thing you measure. All right, so what are the variables? What is our independent variable? Matthew.
The size of the nail.
Yep, absolutely. The size of the nails. What is our dependent variable? Josiah.
The number of paper clips that you can actually pick up with the
That's
electron-
it. That's it. And our controls, which are sometimes called constants, are going to be everything else. Name something. What are some things that we want to keep the same, that we don't want to change? Ari.
The battery and the wire that's being used.
Yep, absolutely. Anybody else have any other thoughts? Matt.
Both agree and I disagree with like some of keeping them, like using the same wire for a couple of reasons, even just being like the wear of the wire or the wear of the battery. Like
So-
like with battery life, even that's a major thing that like if like the first one might be like if you even continue to use the same nail size but continue to use the same battery, over time it's gonna continuously get weaker and weaker.
Yes, you're absolutely right. Those are things that we would have to take into consideration. So for a while, the battery is going to be insignificantly different. Eventually, though, there would be a difference and we would have to be testing the battery. You're right about that. The wires don't really wear out. You know that from your house. You know, your house might be 100 years old and it still has good wires that carry electricity in. So in the extent of this experiment, the wire is not going to wear out. But you're right. Those are all things that have to be considered when you're running a scientific experiment. Yep, good point. Mel.
Humidity.
Yep, humidity, the temperature in the room, all the things that we've mentioned before. So those are all things that we need to either have controls or, you know, we can call them constants, but everything else. All right, we're out of time now. All right, this was fun. Thank you guys for participating. And if you have any questions, send them my way. All right, I'll see you next week.
Bye.
Thank you. Bye.
For coming.